It's 1856. A teenager alone in a grubby London lab is about to accidentally change the world, and he has no idea it's about to happen. London, 1856. A city running on coal smoke, gas lamps, and one desperate medical crisis nobody's solved yet. Malaria was killing people by the thousands, and the only real cure came from a rare tree bark that was expensive, scarce, and running out. This kid's got a plan: build the malaria cure from scratch, using cheap coal tar instead of rare tree bark. Genius idea. Total disaster so far. Another failure. Just black, useless sludge. If you'd been standing there, you'd have told him to give up. Thank God he didn't listen. He's not even trying to fix his experiment anymore, he's just cleaning up. He grabs some alcohol to rinse out the mess. And that's when it happens. And just like that, coal tar sludge turns into the most stunning purple anyone in history has ever laid eyes on. Nobody has ever seen this color before. Ever. Just for fun, he dips a scrap of plain white silk into it. The silk soaks up the color instantly. Deep, rich, completely even. But the real test is still coming. He washes it. He holds it up to sunlight. The color doesn't budge. Most dyes back then faded fast. This one refused to quit. He didn't find a cure for malaria that day. He found something else entirely, the birth of an entire industry that didn't exist yet, and it was 100% an accident. That purple took over the world. Queen Victoria wore it. Fashion houses across Europe went crazy for it. One failed malaria experiment built an entire global industry, practically overnight. So what's actually going on inside that purple molecule? It all comes down to one tiny atom doing something incredibly clever. Let's zoom in. Meet ammonia, NH3, just nitrogen with 3 hydrogens attached. But nitrogen's holding a secret weapon, a spare pair of electrons it's not using for anything. That's about to matter a lot. That lone pair acts like a magnet for anything positively charged, especially a stray hydrogen ion floating by. When it grabs one, boom, that's what makes something a base in chemistry. Now swap one hydrogen for a little carbon chain and you get ethylamine. That carbon chain actually pushes more electrons onto nitrogen, making its lone pair even hungrier. Stronger base. Simple as that. Swap one hydrogen for a carbon group, you get a primary amine. Swap 2, secondary. Swap all 3, tertiary. Same glowing lone pair every single time, just dressed differently. But swap that hydrogen for a benzene ring instead, a flat ring of carbon, and something strange starts happening to that lone pair. Watch closely. That lone pair gets sucked right into the ring and spread out thin. Less available to grab a proton means less basic power. Phenylamine, the weakest base of the bunch, by far. So there's your lineup. Ethylamine's the strongest base, ammonia's the middle ground, and phenylamine's the weakest of the 3. Same nitrogen, wildly different personalities. And that ring, it's about to do something even cooler. That same ring is about to help us cook up one of the most famous colors in human history, and it involves ice, freezing chemistry, and a reaction that has to happen in under 10 degrees Celsius or it blows itself apart. Next up, time to get dangerous. Carefully. This next reaction only works below 10 degrees Celsius. Go 1 degree too warm, and the whole thing falls apart. Literally. This next chemical, nitrous acid, is so unstable you can't buy it in a bottle. You make it fresh, right on the spot, seconds before you need it. Mix that fresh nitrous acid with our ring-shaped amine from before, phenylamine, and something totally new starts forming right on that nitrogen. That amine group transforms into something called a diazonium group. 2 nitrogen atoms locked together carrying a positive charge, and honestly, kind of itching to blow up. Warm that molecule up even a little, and it falls apart instantly, shooting off nitrogen gas. That's exactly why chemists keep this whole reaction on ice. No exceptions. Congratulations, we've just made benzene-diazonium chloride. Stable, on ice, and absolutely ready to cause some vivid, colorful chaos. Now we need a partner for this diazonium ion. Enter phenol, dissolved in an alkaline solution, patiently waiting to react. The moment these two meet, the diazonium ion goes hunting. It's electron hungry, and that phenyl ring looks like an all-you-can-eat buffet. Contact. The diazonium ion locks onto the phenyl ring at exactly the right spot, and the 2 molecules become one connected structure, bridged by nitrogen. And there it is, an azo dye, born in an instant. Same trick as Perkin's purple, just done on purpose this time instead of by accident. Here's the secret. Electrons can now flow freely across the whole stretched out structure like a highway. That bigger highway soaks up specific colors of light and bounces the rest straight back at your eyes. Azo dyes are still everywhere today. Clothes, ink, food coloring, cosmetics. Different coupling partner, different ring, different color. Chemists basically paint with molecules. That's the story of color. But nitrogen's got one more trick up its sleeve, and this one's not in your clothes. It's inside you, right now, holding your entire body together. Zoom into your own muscles, your hair, your skin, and you'll find chains of tiny molecules called amino acids. Let's meet the building blocks of you. Every amino acid has two personalities built into one molecule, a basic amino group on one end, and an acidic group on the other. Total chemical tug of war. Change that one side branch, the R group, and you get a totally different amino acid. Glycine's just a hydrogen. Alanine's got a little more going on. There are 20 of these building blocks in you. Here's the wild part. That acid group just hands its protons straight over to the amine group, right inside the same molecule. Now you've got a positive end and a negative end on one single molecule. That's called a zwitterion. Those two charges pull hard on each other. That's exactly why amino acids dissolve so easily in water and have surprisingly high melting points for such tiny little molecules. Dunk that molecule in acid, and the negative end grabs a proton back, turning neutral. Now the whole molecule's left with a positive charge overall. Now go alkaline instead, and it's the other end's turn. It lets go of its proton, and the whole molecule flips to a net negative charge. So somewhere between acid and alkaline, there's got to be a perfectly balanced middle point, right? So where's that perfect middle point? Picture it like a dial. Full acid on one side, full alkaline on the other. Somewhere in between, this molecule's about to do something weirdly satisfying. Right there, dead center, the positive and negative charges cancel out perfectly. Zero net charge. Chemists call it the isoelectric point, and it's basically that molecule's personal balance beam. Drop these molecules between two electrodes, and here's the fun part. The charged ones start moving. Positive heads one way, negative heads the other. But that balanced one doesn't budge an inch. So below that balance point, positive. Right at it, neutral. Above it, negative. Scientists actually use this exact trick to sort molecules apart. Let's see it happen for real. This is electrophoresis. Real lab, real gel, real electricity. We load our mystery mix of amino acids into one tiny well and get ready to watch chemistry sort itself out. Power on. Right now, invisible to the naked eye, every single molecule in that gel is starting to feel the pull, some toward one end, some toward the other. Inside that gel, it's basically a race. Charged molecules go sprinting toward the electrode that attracts them. The neutral one just stands there, completely unbothered. Even molecules with the same charge don't move at the same speed. Small ones zip through the gel easily. Bigger ones get stuck squeezing through, so size sorts them too. And there it is, completely separated, banded out by charge and size. Scientists call this pattern an electropherogram, and it's exactly how they figure out what's actually in a mystery sample. Alright, amino acids can be sorted and separated, but their real superpower is what happens when they link up. Watch this. Watch closely. The acid end and the amine end link up, kicking out a tiny water molecule in the process. That new connection? It's called a peptide bond. Life runs on this exact link. Two linked up, that's a dipeptide. Add a third, you've got a tripeptide. Same exact trick, every single time, just stacking up, link by link. Keep stacking these links, and eventually you've got a polypeptide. Let that chain fold up into its proper shape, and congratulations, you've just built a protein. That protein folding trick builds your muscles, your hair, even the hemoglobin carrying oxygen through your blood right now. Nitrogen chemistry is literally holding you together. Here's a plot twist. That peptide bond in your body, it's actually just one specific example of a much bigger chemical family called amides. Let's meet the rest of them. Meet ethanamide, a nitrogen sitting right next to a carbon-oxygen double bond. Simple setup, but that one neighboring oxygen changes everything about how this nitrogen behaves. That oxygen is greedy. It yanks the nitrogen's electron pair away completely, almost nothing left to grab a proton with. That's why amides are basically the weakest, calmest member of this whole nitrogen family. Mix an acyl chloride with ammonia, and you get this. Instant white fumes, a genuinely dramatic reaction, and a brand new amide sitting right there in the tube. Boil that same amide bond in acid or alkali, and it snaps right back apart, splitting back into a carboxylic acid and an amine. Same trick that breaks proteins down in your gut, actually. We've covered dyes, we've covered life's building blocks. but we've barely scratched the surface of everything nitrogen can do. Stick around, because this story's about to get even wilder. Look how far we've come. Dyes, amino acids, proteins, all from one tiny atom. But here's the thing. We've been using these amine molecules this whole time without ever asking one simple question. Where do they actually come from? Turns out, chemists have a whole toolbox of ways to build these nitrogen molecules from scratch. Let's crack it open and build one ourselves, step by step. Method 1. Take bromoethane, drown it in a huge excess of ammonia, then heat the whole thing under pressure. Ammonia is about to muscle its way into this molecule. Ammonia's lone pair muscles in, shoves the bromine right off the molecule, and takes its place. That leftover bromine gets mopped up by more ammonia. Boom, primary amine. Do that same trick again using your new primary amine instead of plain ammonia, and you build a secondary amine. Again, and you've got tertiary. Same move every time. Method 2 starts differently. Swap that halogen for a cyanide group instead, and you build something called a nitrile. Carbon and nitrogen lock together in an unusually tight triple bond. Now flood that nitrile with hydrogen using a nickel catalyst or a powerful reducing agent, and that tight triple bond unwinds completely into a fresh primary amine. Method 3. Take an amide, hit it with a powerful reducing agent, and that greedy oxygen gets ripped clean away. The nitrogen's lone pair springs right back to life. Amine, built. 3 totally different starting points, a halogenoalkane, a nitrile, and amide, and all 3 roads lead to the exact same destination, a working amine. But there's one more method, and it's a wild one. Last method, and it's a big one, because this is how chemists actually make phenylamine, the very same ring-shaped amine that started this whole nitrogen story. This one's brutal by comparison. Tin metal, concentrated hydrochloric acid, and serious heat. That harsh combination is about to rip the oxygen right off this molecule's nitro group. The nitro group gets stripped down piece by piece, oxygen replaced by hydrogen, until what's left is a charged intermediate version of our nitrogen ring. Almost there, but not quite free yet. Add sodium hydroxide, and that charged nitrogen finally lets go of its extra proton. And there it is, free phenylamine, same exact ring-shaped amine that kicked off this whole video. Steam distillation pulls the pure phenylamine cleanly away from everything else in the mixture. 4 totally different roads, and every single one ends with a working amine in hand. Remember how that lone pair spread out into the ring? That makes this whole ring unusually rich in electrons, practically begging for a reaction. Let's give it one. Watch this. Phenylamine plus bromine water. No heat, no waiting. Instant white cloud. That electron-rich ring just grabbed bromine so fast it practically snapped it out of the air. 3 bromine atoms, 3 specific spots on the ring, positions 2, 4, and 6, and it happens almost all at once. That's exactly why the reaction is instant instead of slow. And it's not just nitrogen that can pull this trick. Phenol does the exact same thing with its OH group. Turns out, any electron-pushing group can supercharge a ring like this. 4 ways to build an amine. 1 electron-rich ring that reacts in the blink of an eye. Nitrogen chemistry isn't just something we observe, it's something we can actually build on purpose. Every single thing we've covered, the purple dye, the proteins, the amines, all of it is about to come together in one final story. And trust me, you do not want to miss how this one ends. There it is, every single thing nitrogen can do, built from one lonely pair of electrons. One atom, this many tricks. Let's recap the whole wild ride. It all started with one teenager, one ruined experiment, and the most stunning purple the world had ever seen. And it never stopped from there. Amines, remember? Stronger with a carbon chain, way weaker once that lone pair gets sucked into a ring. Nitrogen's basicity in a nutshell. And that ring? Ice-cold chemistry, a wildly unstable intermediate, and one perfectly timed collision later, you've got a dye that's still coloring your clothes today. Amino acids play both sides, acidic and basic at once. Tip the pH one way or the other, and they flip charge. Find that perfect balance point, and they just stop. Sort them by charge and size with a jolt of electricity, or link them up and lose a little water, and suddenly you're building the actual proteins running your body. Amides play it calm and neutral, but give chemists the right ingredients, and they can build a working amine 4 completely different ways. Nitrogen on demand. That's everything nitrogen's taught us so far. But this story doesn't end in a textbook. It's happening in the real world right now, probably closer to you than you think. Fast forward to today. That same nitrogen chemistry Perkins stumbled into is sitting on pharmacy shelves everywhere, quietly saving lives every single day. Painkillers, antihistamines, antibiotics, a huge chunk of modern medicine leans on exactly the nitrogen chemistry you just learned. Same lone pair, saving lives now.
Every wildly colored hoodie, every vivid dress, every dyed fabric on the planet, there's a solid chance an azo dye, born from that same nitrogen trick, made it happen. Every time you eat a meal with protein in it, your body's breaking it right back down into these exact same amino acid building blocks. This chemistry is in your dinner.
Medicine, fashion, the food on your plate, completely different worlds connected by one identical trick nitrogen's been pulling since before any of us were born. That teenager with the ruined flask? He didn't just find a color. He built an entire industry, launched modern organic chemistry, and never even meant to do any of it. Perkin wasn't trying to change the world. He was just curious enough to notice something weird, and brave enough to actually look closer. That's really all it takes. Color, life, medicine. Every single thing we've covered tonight, one atom, one lonely pair of electrons, quietly doing more work than you'd ever guess. If your brain just got a tiny bit bigger watching this, that's honestly the best compliment I could ask for. Stick around, there's a whole universe of weird, wonderful chemistry still waiting. Chemistry's full of these accidental, ridiculous, world-changing surprises. This was just one atom story. Imagine what the rest of the periodic table's been hiding. From one ruined flask in 1856 to everything running through your body right now, that's the story of nitrogen. Thanks for sticking around for all of it. See you in the next one, and next time, we're going even deeper into the periodic table's best-kept secrets.